Lesson 4 is on special triangles, exact values, and the unit circle. So when we're dealing with trigonometry, and next year when we're dealing with more advanced trigonometry in 30-1, there's a couple of triangles that are referred to as special triangles which have some special relationships, and we make reference to them an awful lot. And the first triangle is a 45-45-90 degree triangle. So if this is my 45 degree angle, if this is a 45 degree angle and this is 90, this by default has to be 45 degrees. Because these two angles are equal to each other, I now have an isosceles triangle. So if I was to make the length of this isosceles triangle equal to 1, I'm just setting it at that value, this length here would also be 1. Because it's a 90 degree or a right triangle, I can now use these two legs to solve for the hypotenuse. So I want you to take a moment and find what the hypotenuse of this triangle is. So I would have 1 squared plus 1 squared will equal the hypotenuse squared, or h squared. So h squared would equal 2, and then h would equal the square root of 2. And we'll just leave it as an exact value, so we won't actually try to write it as a decimal. So now if I use my SOHCAHTOA or the XYR that we were working with yesterday, if this is my given angle, what is the sine of that 45 degree angle? What would that equal? 1 over root 2. Do I leave it like that? I would rationalize it, so I'd multiply the top and the bottom by what?
Root 2.
And when I multiply the top and the bottom by root 2, I get
1 2 over 2.
and I don't need to put the 1 in front, so I just get root 2 over 2. What is the cos of the 45 degree angle? So cos would be adjacent over hypotenuse, which would be 1 over root 2 again, which we know simplifies to be root 2 over 2. And then finally, the tan of the 45 degree angle is opposite over adjacent, which would equal 1. So the next triangle that we look at is my 30, 60, 90. So if I drew this triangle, diagram 2 shows an angle of 60 degrees in standard position. If I make an equilateral triangle, that the equal sides are 2 units and a vertical altitude is drawn which divides the equilateral triangle into 2 congruent triangles. If this is an equilateral, if this angle is 60, this angle will be 60, and this entire angle here will be 60. This length is 2, and this entire length is 2. So if I was to drop this altitude down, what does this line do to the base? What is it divided into? Into 2 pieces, and 2 equal pieces, which means if this entire length is equal to 2, this part here would be equal to 1. And this angle right here would be 30 degrees, because I have a 60, a 90, and then what's left over is 30. So what we're going to do first is we're going to determine the length of this altitude, this leg. So I want you to use Pythagoras' theorem and find out what that length, what that altitude is equal to. So when I use Pythagoras' theorem, because it's finding one of the legs, I would subtract. So a squared would equal 2 squared minus 1 squared, which is 4 minus 1, which would become 3. So then the altitude would be equal to the square root of 3. So then if I complete my sine, cos, and tan for this 60-degree angle, sine is opposite over hypotenuse, so the opposite side is at root 3. So I get root 3 over 2. Cos would be the adjacent over the hypotenuse, which would equal what? And tan is opposite over adjacent, which would be what? And root 3 over 1 can simplify to root 3. And finally, if I take this triangle that I had up here, and I spin it around so that instead I put the 30-degree angle along the x-axis instead of vertically, this would still be 60 degrees. This length here, this length here would be equal to 1 because the whole thing is equal to 2. And then this measurement here would be my root 3 because it would still be the same as what I had up above. So now when I look at sine being opposite over hypotenuse, what's the sine of the 30-degree angle? 1 over 2. What's the cos of the 30-degree angle? Root 3 over 2. And then the tan of the 30-degree angle, opposite over adjacent? 1 over root 3. And then if I rationalize that by multiplying the top and the bottom by root 3, I would get root 3 over 3. So the following page takes these special triangles and just lays them out with what the hypotenuse and the sides were. And then redoes the triangles saying what would happen if I made the hypotenuse equal to 1. So if I made this equal to 1, I would achieve that by dividing it by 2. So I do the same thing to the other two sides. And I get 1/2 and root 3 over 2. And guess what? That 30 degrees, that 1/2 was my sine value. That root 3 over 2, that was my cosine value. And then when I get into tan, the same thing. My sine was my root 2 over 2. My cos was root 2 over 2. In the last one, when I divide by 2, sine of 60 is root 3 over 2. Cos of 60 is 1/2. The ones is what I can use to later on make my unit circle, because a unit being equal to 1. If I change these triangles, if I was to multiply this by a value such as, let's say I multiplied it by 5, and I multiplied all of these by 5, my sine and my cos and my tan would still reduce to be the same thing. So if I had made this 5, this would be 5/2, and this would be 5 root 3 over 2. And if I was to determine what the sine of a 30-degree angle is, sine is opposite over hypotenuse. And if I take 5/2 and I divide it by 5, it's the same as multiplying by 1/5. I'm still going to get 1/2. So this relationship of this 1/1/2 root 3 over 2, it will be the same no matter what size the triangle is. My sine 30 will always be a ratio of 1/2. So I can fill the chart in from what we did on the past 2 pages. In other words, sine of a 30-degree is 1/2 over 1, or just 1/2. Sine of a 45-degree becomes root 2 over 2. Sine of a 60-degree is root 3 over 2. So take a moment and fill in the next 2 rows. So if I fill in the rest of the chart, cos of my 30 degrees is root 3 over 2. Cos of my 45 is root 2 over 2. And cos of my 60 is 1/2. And if you notice, the cos and the sine end up kind of being opposite in my 30 and 60, and they're the same in my 45, because with my 45 I have that isosceles. And then my tan of my 30 is my root 3 over 3, tan of 45 is 1, and tan of 60 is root 3. So there's two other angles to consider, and that's 0 degrees and 90 degrees. So if I was to consider a rotational angle of 0 degrees, that means on my quadrant or on my grid, my 0 degrees is right there. And if I said that x, the length of x was equal to 1, y would be equal to 0 because it didn't go up or down. And my r value, my hypotenuse, would also be equal to 1. So if I use my opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent for my sine, my SOHCAHTOA, sine would be opposite over hypotenuse, which is the y over r, which would be 0 over 1 or 0. Cos is adjacent over hypotenuse, which was my x value, which would be 1 over 1. So my cos 0 would be equal to 1. And then my tan, which is opposite over adjacent, y over x, which would be 0 over 1, which would equal 0. So that's of my 0 degree angle. My 90 degree angle puts me right here. And in this 90 degree, my x value is equal to 0, and my y value is equal to 1. And so is my radius, or my hypotenuse, would be equal to 1. So we do the same 3 calculations using these differing values. So I get y over r, which is 1 over 1, which equals 1. So the sine of a 90 degree angle is 1. Cos would be 0 over 1 or 0. And then when I get to tan, I get y over x, which becomes 1 over 0. And what is 1 divided by 0? Undefined. Why? Can't divide something into no groups. So this becomes undefined. So on the following page, there's this chart again, only now we've added in the 0 and the 90. So take everything from the previous page and transfer it all into that chart. So this is what your chart should look like. It says that the chart should be memorized. I'm going to show you a way later on in this lesson that you're not going to have to memorize these values. Okay? Because it's not something that you utilize a lot, except for in the trig unit. So it wouldn't make sense to have to memorize them. Things to notice: sine increases from 0 to 1, where cos decreases from 1 to 0. So they almost have an inverse relationship. And the tangent ratio is equal to the sine divided by cosine. 0 divided by 1, 1/2 divided by root 3, root 2 over 2 divided by root 2 over 2, etc. That's the relationship within those values. So we can use the chart with the concept of reference angles and the cast rule to determine the exact values of trig ratios in certain trig ratios in the quadrants. So if I look first at the sine of a 210 degrees. So sine 210 degrees. What quadrant am I in? Quadrant 3. So what I would recommend doing would be to make a sketch of this. This is my 210 degree angle. Once I've drawn a sketch for it, use that sketch to help you determine the reference angle. So if I'm at 210 degrees, what is the reference angle going to be? And how did you get 30?
210 minus 1.
Now in quadrant 3, is the sign positive or negative? It's negative. So in quadrant 3, we are negative. And we have 30 degrees. So if you remember when we were doing this before, we said that the sine of a 210 degree would be equal to the negative sine of a 30 degree. Now we use our chart. What's the sine of a 30 degree angle? 1/2. So this would be equal to negative 1/2. And if I grabbed my calculator and I went sine 210, I would get negative 0.5. But this is without using the calculator to find that. So we'll do B together, and then I'll let you work on C on your own. So the same thing. Cos of a 300 degree angle. Which quadrant would I be in? Quadrant 4. And in quadrant 4, is cos positive or negative?
Positive.
Positive. Okay? So we've determined the quadrant, we've determined the sign. Now we're going to use quadrant 4 to determine the reference angle. So how do I figure out that reference angle?
$360 minus 300.
So 360 minus 300 would give me 60 degrees. So then I can say that cos 300 is the same as positive cos 60. And then I can use my chart, and what is cos 60? 0.5, it's 1/2 again. Only this time it's positive 1/2. So I want you to take a couple of minutes and try to do the same process for tan 225. So let's look at tan 225 degrees. Which quadrant? Quadrant 3. And in quadrant 3, tan is
Positive.
positive. So then if I sketch quadrant 3 and use that sketch, how do I find the reference angle?
225 minus 100.
And what do I get?
45.
So what I can state is that the tan of a 225 degree angle is the same as a tan of a 45 degree angle. What's the tan of a 45 degree angle? 1. And again, if I grabbed my calculator and I typed in tan 225, it would give me 1 for an answer. So what if we work backwards? What if I give you the ratio and ask you to find the angle without using technology? So in the first one, I have that cos theta equals negative √3/2. And theta is between 0 and 360 degrees. So the first thing to establish, what quadrants is cos negative?
2 and 3.
2 and 3. So I'm going to be in quadrants 2 and 3. Then I'm going to look at my chart, and I'm going to use my chart to determine the reference angle. So on your chart, ignore the negative, look for √3/2 and follow it over to the cos. So look at your cos row and look at where it's √3/2 and then look up at the angle. What angle do I get? 30 degrees. So my reference angle is 30 degrees. So in quadrant 2, this is my reference angle of 30 degrees. What's my rotational angle going to be? $150. So I'm going to take the 180 and take the 30 off, and I get 150. What do I do in quadrant 3? Add the 30, and I would get. So if I was to use my calculator right now, come on. There we go. So if I was to use my calculator, if I type in cos 210, I get negative 0.8660, and this number goes on. If I go root 3 divided by 2, there's the same number. And if I put a negative in front of the root 3, I get the negative 0.8660. So that is showing me that 210 gives me that negative root 3 over 2. If I typed in cos 150, same thing. So if we look at the next one, when tan theta is undefined. So when something is undefined, it has no sign. It's kind of like when it's 0. It's neither positive or negative, which means we need to consider all 4 quadrants, because I don't have a sign to eliminate it to. Now I look at my reference angle. So again, if I look on that chart, I'm looking at the tan row where it's undefined, and then looking up at the angle. And what do I get for the angle? 90 degrees. So in quadrant 1, theta is the same as the reference angle. So in quadrant 1, it's going to be 90 degrees. What is it in quadrant 2? How do I figure it out in quadrant 2?
180 minus 90.
And what's 180 minus 90? 90 degrees. I already have it. How do I figure out theta in quadrant 3?
180 plus 90.
Which is?
270.
And in quadrant 4, how would I figure out theta?
360 minus 90.
And what's 360 minus 90?
270.
So then theta would be 90 and 270 degrees. And again, if you checked it and you typed tan 90 on your calculator, ooh. Let's try that again. Tan 90. Oh, wrong mode. Okay, tan 90. It goes to quit, or it goes to go to. So the error is the domain. That's your calculator's way of telling you it's undefined. And if I did the same thing with 270, the same thing would come up. So last question, and then you'll get some practice time. The point -3 and root 3 is on the terminal arm of angle theta. Without using technology, complete the following question. So draw the angle in standard position and mark point P on the terminal arm. What quadrant is point P in? 2, because it's got a negative x and a positive y. there's point P. So then the angle is this. This is the angle in question because the angle always starts from the initial arm to the terminal arm. So it says state the variables of x and y. So what's x equal to? And what's y equal to? Root 3. So then what's tan theta? Tan theta is y over x, which equals negative root 3 over 3. All we did is take that negative that was in front of the negative 3 and just bring it out in front. So question C says state the reference angle and hence the rotational angle of theta. So my reference angle, if I go back to that chart, I'm looking on tan. Where is tan root 3 over 3? 30 degrees. So the reference angle equals 30 degrees. I'm in quadrant 2. So what is theta in quadrant 2? $150, 180 minus 30. So what I want you to do now is to work on questions 4 and 5. The unit circle. The unit circle, simply put, is a circle in which the radius is 1 unit. That's what the unit circle is. So if I take my unit circle and I transpose these 3 triangles, this is my 30-degree triangle, my 45, and my 60. So in my 60-degree triangle, I know that this length here is 1/2. In my 45, it's root 2 over 2. And in my 30, it was root 3 over 2. And then I can do the same thing with these vertical measurements. This measurement here was 1/2, root 2 over 2, and root 3 over 2. So now if I look at my degrees, at 0 degrees, my x value is 1, my y value is 0. At 30 degrees, my x value was root 3 over 2, my y value was 1/2. At 45 degrees, the values are the same at root 2 over 2. At 60 degrees, my x value is 1/2, and my y value is root 3 over 2. And at 90 degrees, my x value was 0, and my y value was 1. Well, if you look at your chart from a couple of pages ago, what do you notice about the x values in your chart for the 0, 30, 45, 60, and 90? So if I go back to that chart, and I look at my x values, what's your cos? They're my coses. All of my coses were my x values. What do you notice about your y values? They're the sines. So how do the coordinates of the point relate to the measure of the rotation angle? My x's are the same as my coses of those angles, and my y's are the sines of those angles. So if I take this unit circle, which right now is more like a unit quarter, because I only have a quarter of the circle. if I reflected it into the second quadrant, what would happen to my x values? They would turn negative. If I then reflected it down into my y-axis, what would happen? Both of them would be negative, and if I reflected it down here, what would happen? So then if I did that, I would get this. Now, there are some people that feel that you should memorize this. I say no. We don't need to memorize it. Because really what it comes down to is we only actually have two funky looking values. That root 3 over 2 and that root 2 over 2. Well, we've already figured out one of them. Root 3 over 2. Oops. That would help if I did the right one. Is that 0.8660. So if I did a calculation on my calculator and it came back as 0.8660, that's my root 3 over 2. Root 2 over 2? .7071. And then the other ones that you have is that root 3 and that 1 over root 3 for my tans. But there isn't a lot that we have to memorize from the unit circle. The one thing that I do want you to know from the unit circle, however, is that the x values are my coses and my y values are my sines. So that every point on the unit circle can be written, instead of writing it as xy, can be written as cos theta sine theta. What that means is if I go into tan theta, which is y over x, right, opposite over adjacent, well, we just said y was equal to sine. So instead of y, I can write sine theta. Instead of x, I can write cos theta. And that's another one of the points. And ignore this cotangent because we don't do that till next year. Okay, so we'll finish up the examples tomorrow, maybe Friday. So class example number 4 asks us to use the unit circle to find the exact value of the trig ratios with the following rotational angles. Give each ratio with a rational denominator. So if we go back to the unit circle, and we're at 240 degrees, that's this point right here. What we need to remember is that the first coordinate was my cos, my second coordinate was my sine. So xy is in alphabetical order, cos sine is in alphabetical order. So cos first, then sine. So the sine of my 240 degree angle would be negative root 3 over 2. Cos would be what? Negative 1/2. And then tan is sine divided by cos. It's y over x. So this would be sine 240 over cos 240, which would be my root 3 over 2 divided by my 1/2. Or sorry, wrong way, other way around. Would be my negative 1/2 divided by my negative root 3 over 2. So the negatives will cancel out. And I don't know if you guys remember this from when we were exploring divisions. If my denominators are the same, I don't have to flip and multiply. I can divide the numerators. So this would give me 1 over root 3, and the 2's would cancel each other out. So now to rationalize this, I multiply top and bottom by root 3. And I get root 3 over 3. So take a couple of minutes and see if you can do class example number 5 using the unit circle. Thank you, Hannah, for pointing that out. So this one should have been root 3 over 2 divided by 1/2, negative 1/2. The division would still be the same. I can divide the numerators. I get root 3 over 1 or simply root 3. So I don't have to rationalize the denominator for this one. So if I use the unit circle on the next question, cos 135 would be what? Because it would be that x value. What is tan 120? So remember, tan becomes sine divided by cos. So what is sine 120? And what is cos 120?
That's cos 1
Oh, negative 1/2 is cos? Okay. And what is sine? Sine would then be root 3 over 2. So the division, I can cancel out the 2's, and I get root 3 divided by negative 1, or negative root 3. What is sine 180? 0. And then tan 270 becomes sine 270 over cos 270. So what is sine 270 degrees? And what is cos of 270 degrees? And what happens when I try to divide by 0?
What?
You can't. So we say that this is undefined. Tan of 270 degrees does not exist. Okay. In class example 6, A and B are 2 points on the unit circle. If an object rotates counterclockwise from point A to point B, through what angle has it rotated? So, what quadrant is angle A in? Yep. Because this should be a straight line, it's not a negative. So angle A is in quadrant 2. And angle B would be in quadrant 3. So this should be, this would be point A. And then point B would be down here. So if I was to look at my unit circle and I look for this coordinate, what angle does that create? 135 degrees. And if I look at the other coordinate, what is that? 240. So then the question is, if I go from point A to point B, what angle have I gone? So how would I find that? So the angle in red was 240 degrees. The angle in blue is 135 degrees. How do I find the angle in green? Which equals what? What would happen if I didn't have the unit circle to do this question? Could I still do it? I would have to go to my calculator. So I'd have to grab my calculator. and I would be looking at or looking for reference angles. So if I went, this is cos, so if I went cos inverse root 2 divided by 2, I get a 45-degree angle. That's my reference angle. So then I go 180 minus 45, and there's my 135 degrees. Then if I looked at the next one, my 1/2, if I went cos inverse 1/2, I get 60 degrees. So in quadrant 3, I add that to 180, and there's my 240. So you can answer these questions without depending on the unit circle, without either having to memorize it or to recreate it, but by using the calculator and then sketching it out. I strongly recommend sketching these out and getting a visual representation. And that's where I will stop. Lesson 6. Lesson 6 continues from Lesson 5 with conversions between the two systems. Only now we look at what happens when we have square units and cubic units. So if we look at this first investigation, if I ask you to calculate the area of this square, how would you do that? 1 times 1, which equals 1 meter squared. Suppose we were to calculate that same square in centimeters. How many centimeters in a meter? So what would be the area of that square in square centimeters? So 10,000 square centimeters. So these were the same figure, one measured in meters, one measured in centimeters. So from there we can say that 1 square meter is equal to 10,000 square centimeters. And now if we look at millimeters, how many millimeters in a meter? So what would be the area of this square in millimeters?
100,000.
Not 100,000. A million. So 1 square meter is going to equal 1,000,000 square millimeters. So this does confuse students because our conversion factor, we look at it, well, there's 100 centimeters in a meter, so 1 square meter should be equal to 100 square centimeters. Why is it equal to 10,000? Well, I have to think. This 1 meter, if I divide it into 100 columns, that's going to give me 100 columns. Each column's 1 centimeter in width. If I take my width and I split it into rows, I'm going to get 100 rows. Each row is 1 centimeter in its height. So then I'm going to get these little 1 centimeter by 1 centimeter squares. And I will have 10,000 of them now, because I will have 100 rows by 100 columns. Change that into millimeters, I now have 1,000 rows by 1,000 columns. Oh. So let's look at the next one. If I have a rectangle that measures 2 by 4 meters, what is the area?
8 meters squared.
In terms of centimeters, my 4 meters would be how many centimeters?
400.
And my width would be? So what would my area be? 80,000. And if I change that into millimeters, how many millimeters in 4 meters?
4,000.
And the width would be?
2,000.
So the area would be? 8 million. So if I look back, question F says use the ratios to confirm the area of each rectangle. I have that 1 square meter equals 10,000 square centimeters. So that means that 8 square meters should equal 80,000 square centimeters. 1 meter equals 1,000,000 square millimeters. So 8 square meters should equal 8,000,000 square millimeters. Length involves one dimension. Just going this way. So it's a linear measurement. Area is a squared measurement because I have a length and a width, or a height and a base. So I have 2 dimensions. So the area conversion between square units, or for example, to convert from kilometers squared to meters squared, I have to multiply by that square factor twice, or that scale factor twice. So if the conversion from kilometers to meters is to multiply by 100, when it's squared, or sorry, not by 100, by 1,000, when it's squared, I multiply by 1,000 twice. So right here, converting 2.5 kilometers to meters, we multiply by 10 to the third power, or multiply by 1,000. So when we multiply it by 1,000, we get 2,500. If we want to go from 2.5 squared kilometers to squared meters, we have to square that scale factor. So instead of multiplying by a power of 3, it's by 10 to the power of 3 squared, or 10 to the power of 6. So we would move the decimal point 6 places to the right. So my 2.5 kilometers would become 2,500,000 square meters. And again, it's that idea of the rows and the columns. 2.5 kilometers, if that was my length, or sorry, that wouldn't be the length. If my area was 2.5 square kilometers, and I looked at my length and my widths, my lengths and my widths would form rows and columns if I converted it into meters. And there's my square. I have a length and I have a width. So if we look at the first class example, converting from 12 square meters to square millimeters. So remember, when I'm moving to the right on my number line, I'm multiplying by powers of 10. So if I'm going from meters to millimeters, I'm going 1, 2, 3. So that's a 10 to the third power. But because we're talking about area, we square it. And then I would multiply that by 12. So I would have... So to finish off lesson 4, the last couple of class examples, we get to class example number 7, which is using a calculator to determine to 4 decimal places the coordinates of the point on the unit circle that corresponds to the rotational angle of 148 degrees. So if I sketch that out, 148 degrees puts me in the second quadrant. Okay? What do I know about this point P in that quadrant? What are some things that I know about it?
Well, it'll have negative x values and positive y.
Negative x and negative y. Can I figure out what those x's and y's are? What do I know about all of the points on the unit circle? Every point on the unit circle has the coordinates x and y, which can be written as cos theta, sine theta. So if my angle is 148 degrees, my point would then be, so my point of x and y would be cos 148 and then sine 148. And I would use my calculator to determine what those values are. So what is cos of 148 to 4 decimal places?
negative, 8480.
Yes. And then my sine,
0.529.
99 or 98?
9.
How do I know that these started with a 0? Because before you even started telling me what the number was, I was able to put 0 decimal something. How do I know that? How do I know that cosine sine will always be 0 point something? Go back to the definition of cos. What does cos represent? The cosine ratio is what? In SOHCAHTOA, what's cos? Adjacent over hypotenuse. And what is sine? And what can you tell me about the hypotenuse of the triangle?
Well, it's always the biggest.
It's always the biggest side, which means that these fractions are always going to be what we call proper fractions, where the top is smaller than the bottom. So then when I go to divide these, I always get a decimal that's between 0 and 1, or 0 and negative 1. Okay, class example number 8. The point T lies on the unit circle. Determine the value of theta, where theta is an angle made by the positive x-axis and the line that passes through this point T. So if I was to sketch this out, which quadrant would I be in? Quadrant 2, because I've got a negative x and a positive y. So there's point T. And I want to determine the value of theta. The value of theta is this right here. That's theta. So how would I do that? How would I figure out what theta is? And how do I figure out my reference angle? That's my reference angle. How do I use T to find out my reference angle? What is special about these two numbers? They're the x and the y, and what else are they? They're cosine sine, which means that cos theta equals negative 0.8829, and sine theta equals 0.4695. So if I used sine to find my reference angle, how would I do that? How would I find out theta given the ratio? I would do the inverse. And what do I get? Okay. Should I get the same thing if I worked with cos? Yes. But what I need to remember is when I put this in my calculator, because I'm trying to find the reference angle, I'd go cos inverse and I would use the positive 0.8829, not the negative. And check that. If I go cos inverse 0.8829, do I get 28 degrees? So now I have my reference angle. The reference angle equals 28 degrees. How do I find my rotation angle?
180 minus 20.
And what is 180 minus 28?
152.
So the important thing to remember is those x and y values on the unit circle correspond to cos theta and sine theta. So if I have the angle, I can find the points. And if I have the points, I can find the angle using that cos or sine relationship. We have one more example left. Use the chart or the unit circle to find the exact value of the following. So if I use the unit circle, what is cos 300 degrees? What is sine 330 degrees?
Negative.
And if I add 1/2 and negative 1/2, what do I get? I get the same thing if I use my calculator as well. This right here, this sine squared 225 means sine 225 degrees squared. And cos squared 225 would be cos 225 squared. So what is sine 225 degrees?
Negative root 2 over 2.
And what is cos 225 degrees?
Negative root 2.
So if I take negative root 2 over 2 and I square it, the negative will become positive. What is root 2 squared?
2.
And what is 2 squared?
4.
And then I'll get the same thing with the next one. And what's 2/4 plus 2/4? 1 whole. Okay, the last one. What's tan 150 degrees?
Negative root 3 over 2.
Say that again.
Negative root 3 over 2.
Is that what tan is?
Oh no.
How do I find tan?
Sine over 10.
Sine over cos. So what is sine of 150 degrees?
1/2.
And what is cos 150 degrees?
Root 3 over 2. Negative root 3.
So then tan 150, the denominators are the same, so I can divide the numerators. And I get 1 over root 3, or a negative 1 over root 3. When I rationalize it, I get root 3 over 3, or a negative root 3 over 3. So now I can substitute that into this part of the formula. 2 times negative root 3 over 3 over 1 minus negative root 3 over 3 squared, because that's what that tan squared 150 equals. So on the top, when I multiply this out, I will get negative 2 root 3 over 3. And then on the bottom, if I take root 3 and I square it, what do I get? 3. And if I take 3 and I square it, I get 9. So now I have negative 2 root 3 over 3, which is being divided by, what is 3/9 simplified to? 1/3. And what is 1 minus 1/3? 2/3. So now I have negative 2 root 3 over 3 divided by 2/3. 3's are the same, so I can divide my numerators. And what do I notice about my 2's? They can cancel each other out. I can divide top and bottom by 2, and I get a negative root 3. Okay? Remember, this method of dividing fractions works only when the denominators are the same. When the denominators are different, then I can go back to my other pattern of flip and multiply. Okay? So the questions that I would like to add is 9b, 10, 17, and 18.